We're going to continue looking at Gaussian quadrature in this short video, and in particular how we change the limits of integration. So recall our general formula for Gauss-Legendre quadrature. That is that the integral from -1 to 1 of f of x was equal to the sum over n points of weights ai multiplied by function values f of xi. But this is not really very much use in general, because in general we need to estimate an integral from a to b, not from -1 to 1. So how can we use that to integrate an expression like that? So how do we solve the more general case? Well, we're going to do this by making a coordinate transformation. So let's look carefully at what we've got here. We're trying to integrate in a coordinate system defined or denoted by the symbol x. So x goes from a to b in our integral here. We're going to introduce a new coordinate system y, in which the integral can be written as the integral from -1 to 1 of f tilde of y dy. So we need to know the relationship between x and y. So here we have an integral with respect to x. Down here we have an integral with respect to y. And we also need to know what the relationship between f tilde and f is. Okay, so those are the two things that we need to know. So y lies in the interval -1 to 1. That's where we want our coordinate system to be. X lies in the interval a to b. So what we need to do is we need to scale and translate our original interval, that's the x is equal to a to b, so that it scales down to and translates to -1 to 1. So what we're trying to do is this. So we've got to come up with both a scale factor and a translation amount. So what we want to do is we want the transformation first of all to be linear. We're just going to do a linear transformation here. So we're going to say that x and y are related by some kind of linear relationship. X is equal to py plus q, where p and q are constants that we must determine. I'm not going to go through this in this video, but it's straightforward to show that p is equal to b minus a on 2, and that q is equal to b plus a on 2. Or x is equal to 1/2 b plus a plus b minus a y. That's the coordinate transformation that we want. And of course you can also invert this to solve y in terms of x. I suggest that you show this. So if x is given by this expression here, then in terms of our integral f of x dx, dx is just equal to 1/2 b minus a times dy. That comes from this term here. And f of x is equal to f of this expression here. So f of x, we're just using this and substituting that in there for x. So we know what dx is equal to, we know what f of x is equal to in terms of y and dy, so we can then rewrite this integral. So the integral from a to b of f of x dx is equal to b minus a on 2 multiplied by, and so that b minus a here comes from this part here. The function evaluated at x, but x is written here in terms of y, so 1/2 b plus a plus b minus a y dy. So now we've got everything in the form that we need to be able to use Gauss-Legendre quadrature. So f tilde, of course, is just equal to this function here. How do we implement this in practice? Well, I'll do this by way of a simple little example. Let's use two-point Gaussian quadrature to integrate sine of x squared from x equals a to b. So that's the integral that we want to calculate. This is the formula that we've got up here. You need to know how to derive this potentially for the exam. Using this formula, we just see that it's b minus a on 2 multiplied by the integral from -1 to 1 of sine. So this thing here is equal to x. Okay, it's this thing here, but it's x squared dy. And we know that Gaussian quadrature, we need to calculate, or 2-point Gaussian quadrature is given by this formula here. So we need to calculate this function value here, minus 1 on root 3 and plus 1 on root 3. And don't forget the b minus a on 2 in front. That doesn't go away, so we need to keep that. So this then is equal to b minus a on 2 multiplied by sine of all of this stuff here, with y evaluated at minus 1 on root 3 squared, plus sine of all that stuff there, y of 1 on root 3. Those are the two quadrature points for 2-point quadrature.